name is Paul Hopewell. Welcome back to my shed where I make all sorts of components for old bikes, old cars and machines. I also occasionally make prototype components. In this video I take time out to fix an issue that I have with my surface grinder. The issue is balance and the resultant poor finish that I get. I'll demonstrate with two bits of spare material. The first piece of material will be skimmed and I'll show you the end result of the unbalanced wheel. The wheel currently mounted in the surface grinder is the one fitted to the machine when I first got it. I have taken it apart before now in an effort to sort out the poor finish, but due to the time constraints at that time, I put it back as it was with a little packing to try and improve the stone's run out until I had more time to deal with it. What you see now is the spark out operation, which usually improves the overall finish. I'm not using coolant, as coolant can also improve the finish. I'm just showing you what the surface finish can look like if the wheel is not balanced. This is the finish due to poor balancing on my machine. What I do know, and I do know better, is that I should have put it right before now, because an unbalanced grinding wheel can cause vibration leading to a crack or breakage, which has been known to result in serious personal injury or damage to the machine. The lack of wheel balance also affects the quality of the finish product by producing uneven surface finishes or patterns. As you can see, there isn't a great deal holding this cutting wheel in place, nor is there much preventing the wheel wobbling from side to side. All in all, this wheel is very poorly held. For clarity, the spindle wrapping that trued the wheel was removed earlier. This is the condition I received the machine when it arrived on my doorstep. To make matters worse, the spindle is parallel at 25mm. Actually, it's 24.98mm diameter, and the wheel is 1¼ inch bore, necessitating the need to fit bushes. Nevertheless, every grinding machine spindle I've ever worked on or seen has had tapered spindles to ensure a very good level of fit and accuracy, usually provided by arbours of some kind. These arbours in turn have some form of integral balancing aid. As this machine currently has nothing more than a nut and a couple of washers holding the grinding wheel on, I think it's about time I address the problem. My grinder, I believe, is an old Eagle Victor Mark IV wet 18x6 manual table with an attached coolant system. I understand these old machines were normally manufactured as metric machines, but the imperial gearing and index wheels were an option, to which I find odd for an old British machine of the 1950s. Anyway, mine's fitted with the imperial option. But all the cutting wheels that I own are either 1/2 inch bore, the ones for my tool cutter grinder and pedestal grinder. The others at 1¼ and 2 inch bore are the ones that I'll use on my surface grinder. My plan is to make a fitted arbor with an adjustable balancing system that provides linear stability. I need a backing face and bush that is true to the spindle. To hold the wheel in place and to hold it firm requires a washer of equal diameter to the backing face. Both the backing plate and the washer also need a recess near the bush. To hold the washer in place requires nothing more than a thread. The thread I chose is roughly the same pitch as the thread on the spindle, which is 3/4 inch BSF, roughly 12 TPI. 12 TPI also works nicely with 1¼ inch and 2 inch spindles. Ignore the fact that I put 1 inch on the board, it was only an approximate size before I measured it properly with a mic. The spindle rotates anti-clockwise, requiring a clockwise thread on the nut that I planned to hold the washer in place. But I changed my mind in favour of threading the washer. I also reckoned that this washer could be nipped up using a couple of blind socketed holes to be tightened with a simple 2-pin tool. As I mentioned earlier, the arbor is also going to be responsible for balancing the wheel as well as holding it firm and true. There are as many ways of balancing grinding wheels as there are craters on the moon. I've chosen to use the dovetail method, for no other reason than I'm comfortable with this method. I could have used a ring of holes and grub screws or 2 eccentric washers. I could just simply remove material from the heavy side of the grinding wheel, all of which would probably have been a whole lot easier. But as I've mentioned in the past, I don't do easy. To do the dovetail groove, I plan to cut a slot using a shaped trepanning cutter. Then I plan to cut either side of the dovetail using 2 profiled high-speed steel cutters. What I do know about cutting curved or circular dovetail slots is that if one is making many dovetail grooves, consistency is key. And to maintain consistency, a profile gauge is top of the list of items required. That is, it will be needed to ensure that all dovetail grooves are the same profile, even if they aren't exactly the same diameter. I'll explain more about this later. After many hours of calculating and recalculating, my sticker board ended up covered with all the markings of what I call a plan. This is the surface grinder spindle dimensions. This is the arbor's general dimensions. This is a sectional sketch of the arbor and spindle together. This is the sectional drawing of the balance weight ring. This area covers the operation planning. Finally, here is my required tools list, with one of the 2 checking gauges that I need. This one's a double-ended gauge. The other one, not shown here, is a simple 10mm slip gauge. The first part I'll concentrate on is the main arbor body. This was finally done in 4 operations. I received a sticker a little time ago. I could have released it on my last video, but I decided to wait for this video before I put it up. It's a sticker from My Little Mule. I've seen his channel many times and I thoroughly enjoy watching his exploits. I went to his site on more than one occasion to watch his take on refurbishing a South Bend 13 lathe. He has a very sound methodology with all of his projects and is well worth a visit. Just pop along and give his channel some support. Thanks, Greg. Cheers. If you want to get a sticker on the board, drop me a line or let me know in the comments. Right, I'm only going to get the arbor's main body machined in this video. The rest of the arbor's components will be made on the second video when it's complete. And for the record, this is the lathe's first outing and it's the start of my learning curve using it. While I was making this video, much of my time was taken up on another project, the studs video that I previously released. The material I used here is nothing more than low carbon steel bar offcuts. You'll see that it doesn't machine all that well. I chose high speed steel tools for this operation, firstly because the cutting speeds are slower. Secondly, the material removal rate was quite useful at this speed. And thirdly, I needed to hover around the E-stop button. You'll probably notice in some scenes that I'm working on 2 different spigot sizes, so don't be surprised if you notice one spigot bigger than another. In one of my lathe rebuild videos, I tested the amount of run out of this chuck to be very good. Better than good, really. Oh! But as I said at the time, that it must have been a fluke. And it was. However, I do get to around 2 thou run out, which to be fair is good and I can work with that. After finishing the face, the OD was reduced to 87mm, just enough to clean the rusty skin off. Followed by a generous chamfer, more for aesthetic reasons really. Oh well, that can happen. This is where I started the trepanning, or digging out the slot for the circular dovetail. I used a high-speed steel hand-ground tool that I found at the bottom of a bunch of stuff from eBay, and all I did to get it to a useful state was to hand-cut an external radial relief and brighten up the cutting edges. To be honest, I wasn't really certain it was going to be strong enough. This is where I used the first of my checking gauges that I made from some 3mm bar. Making these gauges involve a bit of maths and a lot of time, so apart from a brief explanation on usage, I won't go into how I made them. After all, this video's long enough. and I've got lots of people banging on my door wanting stuff doing. The idea is to maintain the dovetail's profile across all 5 arbours. One can use a vernier, but a checking gauge is easier to use and will aid producing a uniform dovetail slot no matter what diameter it is. I don't think anyone can claim to be able to hit exactly the same diametric size on multiple items every time, especially with a vernier. Give yourself a gold star if you can. A checking gauge in this instance is a plate that has been shaped to the required dimensions and checked. The edges of that shape have also been roll edged to prevent inaccuracies during use. Using these gauges help to maintain the correct dovetail profile, even if the diameter of the very first cut is not to size. I'll briefly explain how these checking gauges work. The idea is to first get the profile that you require somewhere near, then to try twist the profile gauge through. The process is simple. If the gauge doesn't rotate through the machine profile, then you need to remove more material. If the profile gauge does rotate inside the profile, then you've taken too much off. If the profile gauge just rotates through with friction, it'll do. So if the diameter is a thou or two out, the profile can still be good. Another thing, if the slotted recess is the right size, then the telltale witness should disappear at the same time. That is, the profile cutter has removed the right amount of material. Mind you, a small witness may still remain near the edge of such a profile for many reasons, like a burr for instance. This is just a little too tight. One more thou should do it. These dovetail profile cutters and the first side of the dovetail gauge were shaped on my Clarkson cutter grinder. They were each shaped to cut one side of the dovetail, and just so they didn't break off, the underside was relieved to prevent the tool from bottoming out and thereby preventing the tool from being damaged. The next task is to drill through using the standard pilot drill and then the sizing drill. The finished bore is to be 25.02 to 25.03. The biggest drill I dared use was 22mm. It worked and the bore remained less than 22.2mm after drilling. But I wondered how true it was and by how much did it wobble. It remained to be seen till after the roughing and finishing of the back face recess. This back face recess is intended to move the arbor as far back as possible. In doing so, allows me to use any of my cutting wheels from 12mm to 25mm without compromising the locking nut's integrity. Now for the moment of truth. Did the drill stay central? The answer? Nope. No, it didn't. It did wonder, only a tiny bit though. Thankfully, after the first cut with the boring bar, it cleaned up, leaving me 3 more goes to get the bore to size. To be honest, one small part of me was whistling Dixie on the last cut because the material was so bloody awful to machine. I missed the bottom limit by 0.01mm, that's 4/10. I daren't go down it again because it was likely to machine oversize, so I did what any home engineer would do, and that was I buffed it with a rotary buffing wheel. And it worked, top limit and a lovely finish to boot. And because this turns out good, I buffed out all the rest of them except for one. It nearly ended up too big in the bore, and after dropping it in a bucket of cold water for a few minutes, it was mid-limits, and the following day it was top limits. Well, I did say the water was cold. After a little wiggle, they all slid onto the spindle with a satisfying click as they reached the back of the spindle. Now, in order to make sure the spigot and the spigot face are true to the bore, I'm going to use a bit of old-fashioned technology. I'm going to make a tapered mandrel. The idea is to force the arbor over the mandrel with a press until it's locked on, then machine the remainder between centres. Then, when I'm happy with everything, I'll unload it with the press. Well, that was the plan anyway. This was the end and centering procedure. The bar I used was a bit of 1-inch mild steel, rusty mild steel, probably medium carbon stuff. This gave me a little worry. I'd forgotten about all those videos I'd watched about the screw-on chuck staying on for good. There's no prize for not trying, so I put the chuck key in the chuck and gave it a firm tug, and it spun off despite all the machining I'd done so far. I did lightly oil the thread though before I fitted the chuck, and perhaps that helped. I fitted the faceplate and a number 4 Morse taper. I put the drive dog on the 1-inch bar and then I mounted the bar into place. Remember, this is a 1-inch diameter bar, and I need a 1/1000 in 6-inch taper along its length. But I've only got 0.4 millimeters to play with. That's just over 1/7 a side to play with. Bearing in mind, the machine has just machined 5 near true 25mm bores, and I say near true because I got a very small taper in all 5 arbors that was bigger towards the tailstock. And I need a taper smaller at the tailstock. After lightly skimming along its length, I took a measurement and calculated roughly what I needed to do at the tailstock to get me somewhere near. Then, after another skim and a final adjustment, I was rewarded with a taper that was inside my workable tolerance. After assuring myself that the taper should be okay, I put a couple of marks indicating where the maximum limit should be along the bar. Then I pressed the first arbor on. I didn't use oil or grease, I just pressed it on. Every creak and click made me wonder if I'd gone too far. My press is a 12-ton press, and I reckon I was near 5 of them when I stopped. I put a mark on the shaft and pressed it some more, and at about what I thought was 8 tons I gave in. You have to remember that when the outside diameter was machined, I was holding the material by the dimensions I'm about to final machine now. And after giving the OD a very slight skim, there was in fact a small difference. Enough to see it on the chamfered edge when viewed from the other side. This means that the balance weight dovetail groove is no longer concentric to the ball, meaning that the arbor isn't balanced. Am I bothered? No, because the amount of difference it would make when the wheel is mounted on it and locked in place amounts to diddly squat. Happy with what I got, I machined the back face, and I also cut in and created a recess. And I dug the tool into the corner to create a relief recess. The stones with the 2-inch bore simply glide onto the 2-inch hub. Now it's time to cut the threads. To stop the mandrel from moving, I bolted an extra restraining bracket firmly set in the drive dog with enough pressure to hold it firm but not influence the outcome. While truing the thread cutting tool, I was beginning to get butterflies, because these hubs are giving the machine a bit of a shakedown, and I hope everything I put right during the lathe rebuild is up to the job. The half nuts and the lead screw indicator are the last items to be put through its paces, so my fingers are crossed. And my toes. When I first engaged the half nuts, I sort of snatched at them, bang on the numeric marker, and I missed the mark. And then I had another go and engaged too light or right at the top of the bite, so I disengaged it once more. The third time I popped it in beautifully, and now I know when the half knots are ready and how fine the engagement is. And now that I've used it in anger, so to speak, it's as slick as a Swiss watch. At the end of the thread I decided to let the cutter dwell to create a recess at the end of the thread. As I mentioned earlier, the pitch was set to 12 TPI on both the 2-inch and the 1 1/4 inch diameter hobs. I used the lathe file to dress the tops of the threads off. I know the visible side of this file looks a bit munted, but it's perfectly sound on the other side. I reckon the previous owner used to hold this file stationary over a revolving component. When I pressed the first arbor off the mandrel, I wasn't sure if the two components had marred each other. In the end, both the arbor and the mandrel were unharmed by the forces that I used to fit them together or push them apart. Anyway, that's the first part of the grinding wheel arbor video complete. Look out for part 2 and the meat grinder. Apart from a small tip at the end of this video, that's all for now. Thanks for watching. Bye. This might be of interest to some of you. It's a variation of Murphy's Law that is often followed with a cursory expletive that I believe that most engineers are familiar with. And it's what can happen when using a profile tool similar to what you see here. One can often be met with the inevitable involuntary knurling caused by vibration. It almost always happens on the very last turn of the chuck, just before you disengage the cutter while finishing. I had this happen to me many times in the past. The trouble is, the bigger the profile, the greater the risk. What I do is put the tool back next to the workpiece just slightly shy of cutting. Then, if possible, turn the chuck at the slowest possible speed you can. Ideally as slow as the 1 minute hand on a clock. Problem is, you'll probably fall asleep doing it, so I suggest turning the chuck slow enough to peel the swarf off, so that the resultant swarf chips are shiny. Doing this at a very slow constant speed also leaves a very nice finish on the workpiece. You may have to tap on another half thou or so and do it a couple of times before it's good enough. And sometimes it ends up looking like a mirror finish. It's much easier if you are using a sharp high-speed steel profile tool. It's much harder if you are using a sharp carbide cutter and you might need a longer wrench to pull the chuck around. If you use an insert tool, then best of luck with that one, especially with a negative rate tool. For that you'll need to do it under power, and I don't know many machines that can turn at less than 1 RPM. You can also improve the finish by drizzling coolant over the point of contact. The bigger or more complex the profile, the more effort will be needed to turn the chuck slowly. I hope this was of interest to you. Bye for now.